Hey, what's up, guys? Chung here again. And today, I want to talk about this LeetCode problem, number 994, routing oranges. Medium, medium problem. It's very, I think it's an interesting problem. Okay, you're given like a 2D grid, and on each grid there will be only three options here, either 0, 1, or 2, where 0 representing an empty cell, 1 representing a fresh orange, and 2 representing a rotten orange. Every minute, any fresh orange that is adjacent four directionally to a rotten orange becomes rotten and returns the minimum number of minutes that must elapse until no cell has a fresh orange. If this is impossible, return -1 instead. Yeah, it's pretty straightforward, right? So at the beginning, let's say, assuming, for example, this example one here, let's assume you have a rotten orange at this position 0, 0, and on the next second, on the next on the next minute, the adjacent uh, fresh orange will become a rotten orange. So basically, this is like a plague, right? A disease that's spreading to all the oranges in this case, and until all the adjacent oranges have been have been traversed essentially, right? I mean, so by this time, I believe everyone can see this is like a breadth first search problem because it satisfies all the signatures of a breadth first search problem. You have four directions, and then you need to find the minimum numbers. That's I mean after traversing to all the oranges. Okay, and I think it's just one more thing to be careful here. It asks you to return -1 if it's not possible to mm, if it's not possible to make all the fresh oranges to become a rotten or to become the rotten orange, become rotten, then I think in the end we simply just loop through. We can just do a final check in the end. We just loop through this 2D board, 2D board, 2D board, and when we see a fresh orange, we simply return -1. Okay, pretty straightforward, huh? Right. So the main code for this is uh, just a standard standard breadth first search template. Okay, let's try to implement these things here. Okay, directions, right? It's very standard breadth first search. -1, 0. Okay, we need to define the four directions, right? That's up, so that's down, and so this is left. Okay, left, and this is right. Okay, then we're gonna have like the length, the rows and the columns. Okay, the rows and the columns. Okay, 0. Mm, okay, so the grid is at the length of the grid is at least 1, so we don't have to check this M and N here to do a sanity check. Cool. So other than that, we need a queue, right? Since we're going to do a breadth first search, collections DQ. Okay, DQ. So where to start, right? And to start with, we start with all the rotten oranges here. And remember, even though in the example here we only have one like rotten orange, but it doesn't say that there will only be only one rotten orange at the beginning, which means there could be like two rotten oranges, right? So for in that case, so first we're gonna loop through the grid here in range M, right? For J in range N. Basically, if the grid I j is 2, right? Then we simply add, mm, append mm, append this this orange to our queue. So after this for loop, a nested for loop here, we have all the basically we have our starting point where we have all the rotten orange added to this queue here. Okay, now let's do a while queue, right? So that's the BFS search. And for BFS search, we're gonna do a for in range length of queue. Okay. So and then current j, right, equals to the queue dot pop left. Okay. So this is the things you need to be careful. So for the BFS search, we add to the tail, but we always pop we always pop at the beginning or at the front. Okay, so and for each of the I here, right, we do a loop here, right, for directions in range, sorry, in directions. Okay, directions, and then the new I become the D current I plus D0. Okay, and new J goes to current J plus D1, right? And then we just do a boundary check here. Mm, and and okay, and what? So for the BFS search, if you know the template, we have to somehow we don't want to basically end up in the infinite loop here. That's why we have to mark the basically the node we had previously visited before. But in this case, we can simply mark that we can simply mark all the nodes, the visited nodes to 2 here. 2 is the rotten orange, right? And we only add the new node to the queue if it's a fresh orange, right? Basically, that's what I'm doing here. So, and if the DP and also if the DP at new I and new J is 1, okay? So what I'm doing here is if the new I and J are within the 2D board and this grid is is a fresh orange, then it means that okay, now it's his turn to be to become a rotten orange. So that's why I do a q dot append new I and new J, right? And after adding this one to the queue, don't forget to set this fresh orange to the rotten orange. Okay, set this one to 2 here. Yeah, so basically this is basically the BFS search here. Okay, the BFS traverse, but in our case we haven't set this answer yet. I mean we can simply do an answer dot plus 1 here, and then uh, but there's a like small issue here. I mean, in the end, we simply return the answer, right? So basically, that's gonna be our answer here. But there's like a small uh, uh, issue here. Let's assuming, mm, yeah, assuming in this case, okay, assuming in this case we have like 0, we have empty space and only one rotten orange, and in this case, uh, at the beginning, the queue will have this one rotten orange, and after traversing this queue here, we didn't see any fresh orange. That's why we'll be ending. We'll stop this while loop here. But we're adding this. But we're adding these answers. We're adding these answers by 1, right? So now we'll get 1 instead of 0. Mm. I mean, you can argue, we can always do a answer minus 1. I mean, this might work, right? But this answer minus 1 also have another issue. Let's say we don't have anything in this queue here. Okay, I mean, let's say we don't have any rotten orange in this 2D board. Everything is fresh, or everything is like, mm, no, sorry, not everything is fresh. Or let's say everything is an empty cell. And in this case, the answer will be 0 because we never get into this queue here, but we do answer minus 1. So in this case, but we are expecting 0, not minus 1. So we have to deal with that special case as well. So I think one of the simple solution here is that before doing the answer, before increasing the answer here, we can simply do a check here. Basically, if the queue is not empty, then we increase the answer. So that I think that aligns with the description of the problem. You know, every minute, right? Basically, every time after uh, after looping through uh, the current layer, okay? And if the queue is not empty, then we know, okay, so there will be more fresh oranges becomes rotten in the next minute. That's why we will basically increase the minute by 1. Okay, so that can solve all our edge cases. And yeah, I think one thing we haven't covered here is the check for the minus 1. So an easy check is that we simply do another for loop here. We loop through the whole grid here one more time. And if the grid I and j equals to 1, we simply return minus 1, right? Because we have already basically infected all the uh, all the fresh oranges within this while loop. I mean, if there is still some fresh oranges left, then which means that's something we cannot. I mean, it means those are the oranges we cannot reach, right? From this rotten oranges. That's when we need to return minus 1 here. Otherwise, we simply return the answer. Mm. Yeah, I believe this should just work. Let's try to run this code here. Di direction, direction. Okay, directions. Okay, so this test pass, this test case passed. Let's try to submit it. Yeah. So and yeah, pretty straightforward. Okay, yeah. How about the time and space complexity here, right? So mm, I think here it's like O of m times n, right? That's the for loop. How about this while loop? So the while loop we have, yeah, so the while loop is also O of m and n because since we will not reprocess uh, the node for multiple times, basically we will be only for the worst case, right? For the worst case, let's say all the oranges will become rotten. So that means we'll do this pop like m times n times in total, and we'll do this like for each of the m times n, we'll do this for loop. That's gonna be 4, right? So um, times 4, right? But still, since this 4 is a constant, still the time complexity for this while loop is O of m times n, and and the space complexity, right? The space complex, and here is also like another O of time n. So uh, in total, the time complexity is still O of m times n. So the space complexity is also like O of mn, right? That's the size of the queue here. Yeah, actually, so the size of the queue, it might be smaller than m times n because we're doing like this the BFS search. So every time we're only processing one layer of data, but still, I mean, still, it's a it's amortized O of m times n. Hmm. Yeah, cool. I think that's it for this problem. Yeah, it's just like it's very classic, typical like BFS search problem, and it's just like see anything until here. It's just basic BFS search problem, the template, and we just add one more final check here to handle this -1 case. Yeah, okay, I think that's it for this problem. I hope you guys enjoy watching the video and stay tuned. See you guys soon. Bye bye.